Hello everyone, I think we can start. So today I'll be talking about my journey into researching SSL pinning the last few months. This has mostly been focused on trying to find a way investigating how we can potentially bypass SSL pinning as well as other measures from a perspective where we don't necessarily know what's going on in the application. Maybe it's a native application, maybe there's a lot of reflective loading or such involved, and in general just to get a better understanding of how the TLS stack on a mobile application works. For this research I specifically focused on an Android environment, though some of this is also directly transferable to iOS. So firstly, just an introduction, we're going to run through the normal ways you typically do SSL pinning, the typical bypasses we use for those, then we'll move on to how memory patching works and why I thought that might be a potential approach to do, and then the future work that I'm planning to do from here and the many more questions that I got after only barely getting my initial ones answered. So, in terms of who I am, some of you might have heard of me or not. I work for Orange Cyber Defense. I'm also a staff member on Hack South and a organizer for BSides Cape Town. So just before we start, a disclaimer. I don't consider certificate pinning or the lack of certificate pinning as a security vulnerability. It's rather a more defense in-depth measure rather than a vulnerability, the lack of it. And in our case, we assume you already have direct access to the device, so this approach does not constitute a vulnerability per se or a new bypass that can actively be used in an attack or such, but rather just to aid reverse engineering and maybe malware analysis or such. So firstly, what is certificate pinning? It's basically the act of using some token for verifying that the certificate you are getting from the server is what you expect it to be. This is typically done when you want to further measure other than verifying the normal certificate chain. And once again, it serves effectively the purpose of providing additional protection. So let's say a certificate authority is compromised or some of the other measures to verify the chain fails. Then there's some typical nuances that are important here with certificate pinning. Many times what is referred to as certificate pinning isn't actually certificate pinning. So hostname validation, your chain validation, the trust store certificate validation, all of those can involve certificate pinning, but many times it's not actually certificate pinning that's taking place. There's just other verifications, and it might appear that you're not getting traffic because it's certificate pinning, but in technicality it's not. Now, in terms of issues with implementing SSL pinning, Con and Andre showed us nicely how not to do that and the many other issues that can occur when you try to implement certificate pinning and how that can break all the normal other protections that are usually in place. So just a rough introduction. This is effectively the handshake that takes place with TLS. It's not too important. All we need to know here is that the server is going to send us a certificate chain. The client's going to verify that, and then the actual encrypted connection is going to be established. Here we have an overview of the JavaScript socket extension. This is just the different libraries that are used to construct the TLS connection. Most of them are not really that important. We're going to look at the trust managers as well as the SSL context. But most of what I looked at is not within the Java environment because I wanted to try and get a more generic approach that applies across different programming languages and implementations. Now, in terms of the typical implementations for certificate pinning, at least the ones I've seen in my experience, it's typically done through a hash, or it can be done through a full certificate pinning, but most typically it's just a hash, either SHA-56, SHA-1 or MD5 of the public certificate of of one of the public certificates in the certificate chain. Here's another example from a reverse engineered application where it uses a full public certificate and it just loads that from the resources. So in this case, it's far easier to just patch the actual application, or maybe patch when it reads the file from the file system. So I didn't bother too much in terms of these certificates, and it becomes quite a bit of a race condition when you try to replace these certificates just because of the size. Now, just a very rough overview of how a certificate chain looks. We have a certificate authority that we're starting with. We have maybe one or more intermediate certificates, and then we have our leaf certificate. That's it, and that's basically what's important to us. Now, in actuality, it looks more like this, where we have, for example, our ISRG root X1 root certificate, a R30 intermediate certificate, and then the leaf certificate, which is a wildcard certificate in this case for bad SSL. And at the bottom right, you'll see the public key value there, 0B9FA, and that is the raw hex value for that. Now, if you take from the previous slides, if you take that hash, that SHA-56 hash there, that's actually just base64 encoded. If you decode that, you're going to get the same value. Moving on, I use this specific application, SSL pinning demo, that I got off GitHub just for demonstration purposes. It provides a myriad of different SSL pinning methods as well as certificate transparency. For this talk, I won't be considering certificate transparency, as that's not really SSL pinning. It's a bit of a different method of validating the certificate itself. Then, the typical bypasses that we use when we're talking about an instrumentation perspective and not from an attacker perspective where we want to actually compromise the communication. We're assuming we have full control over the device already. Typically things like Frida is used, or patching the IPA or the APK application, for example, modifying the network security config or removing the hard-coded hashes there, and then of course objection. So why memory patching? I mean, we already have existing ways to bypass SSL pinning. Why just another one? Well, because I wanted to find a more difficult method to basically accomplish the same thing less reliably, because apparently I've had too much fun in life. Yeah. But more specifically, strings are quite easy to find in memory when they're not encrypted or such. They have a set length, especially because we're dealing here with a hash. They have predetermined lengths that don't really change, so we didn't really need to make a string either longer or shorter. In which case, if we had to do that, it would become quite a bit more complicated, because if you're dealing with a framework like Java or other programming languages, it's a more complex data structure, not like C, which is the null terminator. So we'd also have to override the length of the string, which things get quite a bit complicated when we assume it's a black box and we don't know what's going on there. Issues that we might have if this was not the case, especially in terms of Java, is Java's primitives are immutable, which means once it's created, the actual value in memory, it doesn't get changed. So if you have a string in Java and you change that string from the variable, a new memory address gets allocated and the new value is assigned there. What this means for us is if we want to track a specific variable across 2 points in time, that's not really possible with Java, because the original one is going to still have, the original memory value is still going to have the same value, and even if we change that, it's not going to affect what the actual value is reflected within the code, because a new memory address has been assigned to that. But because we're dealing with effectively constants here, none of this is a problem. We have static strings that have a set length, they're stored directly and they never changed, so we don't have to deal with any of these problems. So when we're dealing from a black box, one thing that becomes important is knowing what the application actually connects to. If we're not looking at the source code, we don't know what server is being used, so how on earth are we going to figure out what the string is in the first place to patch with memory? Like, we wouldn't know. Now, one approach we could use is doing DNS resolution, maybe forcing the phone to use a DNS server that we own. We could potentially do some other attacks with that as well, but using that we can figure out what servers the device is trying to connect to. Another option, that let's say the device is using IP addresses directly for some reason, we could also just rook the raw sockets on the Android device. And I'm specifically referring to the raw sockets, not Java, because if we have other frameworks such as Java, such as Dart, which is employed by Flutter, you're not going to see that because it already has its own implementation of TLS and doesn't use the Java JSSE stack. So we can hook on socket level to get the server that's being connected to. Now that we have the server address, how do we go about figuring out what the actual hash is that's being pinned that we want to find? Because currently, once again, we're dealing with a black box here. So the first thing you can go about is just using this OpenSSL command. It might look complicated. It's fairly simple. As you can see there, it's connecting to ess384.badssl.com. That's just the domain in this example. All this is doing is pulling the certificate chain using OpenSSL, and awk is just being used to dump that into 3 or however long the chain is PEM files. That's all effectively does. Just pull the certificate chain. And then we have another one here that basically goes for each of those certificates files. It takes them, and then on the 4th line there, you'll see it calculates the SHA-256 digest, and then it just pipes it into or converts it to base64. You can also just do that with a base64 command. And similarly, you can use this for all the other different formats, SHA-1, MD5, just to get all the different hashes. This is just an example. Now, if we look at the bottom there, we will see the base64 encoded versions of them, and that last one may or may not be familiar, look familiar. So that is actually the hash that was used in the slides at the beginning for the certificate pinning. I have already seen that hash way too many times. Now, if we move over to our implementation here, this is just an example Frida script to now do the actual patching. If we look at the top there, we firstly begin with the SHA-256 hash of our burp certificate. Because in this case, we're using burp as an intercepting proxy. This is arbitrary. You can obviously use whatever you want. And we just need the actual certificates hash. You can calculate this once again using the same OpenSSL commands that I showed in the previous slides. So, okay, now we have the SHA-256 hash. We have the list of hashes from the website. So if we go back one, okay, this is not going back. If we go back one, we have on the hex there, the 3 hex lines. Those are the same ones we have in this script, just the first part of them, because we don't really need to look for the full one. They're fairly unique strings. And then once we have that, we basically find the areas in memory that we have read-write access to. In this case, just the specific first one. Depending on the application, where the logic lies, this is going to differ. It might not be in the main module of the application. This command, I believe, is probably just going to fetch the main module. So just, as you can see at the end there, that 0 index, I just fetches the first index that's returned. So that's going to be the main module of the application. And we have read-write access to that in this case. And then we're just going to loop over all the full certificates, the array that contains the certificate hashes. And this is now of our target server. This is the ones we pulled. And then for each of those, we're going to use the memory.scan command of Frida to locate that hash within memory. We're searching from the module.base size of module.size, and then obviously looking for those hex values within the RAM memory of the device. And once it finds those, we just override the bytes of those with our certificate hash. Now, this is a bit of a example implementation. It's probably going to not work in a lot of cases. This only works, for example, when you're looking, or when the device is trying to pin a single hash, because what this is effectively going to do is it's overriding all the hashes within the chain. So if 2 hashes are checked, this is obviously going to fail because we're just overriding all of them with the same value. Then moving on, so this is what that typically looks once we execute it. Once again, on the right side, we have the certificate pinning example application. Just a rundown effectively of what that does. So the first two there, the unpinned request and the unpinned web view request, those are, as they say, the unpinned request. Just the context in which they make the request differs. The second and third one relies on the security config file, the XML file within the application, both a SHA-256 hash as well as the full certificate hash of the certificate. The reason I didn't bypass those is because the data structure they use is slightly different, and I didn't really care too much because they are, as I said, they're using the network security config, which is a very easily accessible file. It's not encrypted. We know where it is. So it's not really of importance or any practicality to override these when you can just modify that plain text file. And then we have the third one there, which uses the OKHTTP pinned requests. We have volley, which uses a bit of a additional logic to validate the full certificate chain. This does verification both on Java side as well as the native libraries of OpenSSL and such that are used on Android. I'll get to more specifics later on. And then a lot of the next ones use certificate transparency, CT as noted there, so we don't really care of them. And then we have what's called the raw custom pinned request. So this just opens a raw SSL socket, gets the certificates of the server, and validates them against this hash. Now it's interesting, this is considered as the most difficult to bypass, but because we're using a fundamentally different approach to attack this, in quotes, we don't have that problem because we're not trying to hook functions here or known libraries, rather we're attacking it from a memory perspective and assuming we know nothing about the application. Then, moving on, while I was at this, also, as Leon reminded us in his talk last year, I thought I both needed a framework for this, and I had already programmed a lot of the scripts and such that I need to search for things in memory and replace them. I thought I might as well add this to one of the tools I'm using constantly just to make my life easier, and then why not also submit that so other people can also find value in that, because I mean the work's already been done at this point. So getting over to OpenSSL. OpenSSL I found is employed very, very vastly. It is used by a lot of different frameworks, not directly but indirectly. So even Android uses, as a default, its TLS manager is OpenSSL, sort of. So by default, it uses Conscript. Now, Conscript is a Java library created by Google, and Conscript makes calls to Boring SSL, which is a C library. Now it does that through the Java native interface, and then the Boring SSL library is a fork of OpenSSL, through which half of its calls still rely on OpenSSL. So the core point here is the logic or the base data structure that is used here is the same across a lot of different platforms. Now, for interest's sake, I also looked at Dart, which is used by Flutter, and that also uses boring SSL, although it doesn't use conscript, which once again uses OpenSSL. So theoretically, if we can understand the data structure that's in use by OpenSSL, we can find that in memory, patch that, yeah, bypass that. Simple, right? Yeah. So starting off, I hooked up a debugger and started looking through the Java functions. In this case, this is deep within conscript. I learned a lot of interesting things here. So yeah, you'll see the mContext variable that looks like a weird long integer. That's actually a long value because Java doesn't have pointers. So that's actually a pointer value to the C data structure that they're storing in a long within Java. Why? Because all of the OpenSSL functions that make modifications or that take data, you need to pass the mContext value or the CTX, as it's called in the C world, value to those functions for it to be able to retrieve that, because all of them are static. So if we start looking at the data structures within C, it looks something like this. So this is specifically the struct that mContext points to. There's a whole lot of values there. Luckily, unfortunately for us, we only care about the first one, in this case, firstly to define this, which is the certificate info. Because if it was any of the other ones, the lookup gets a bit more complicated, because once again, we're dealing in the context of memory, yes, so we're working in offsets. All of these are raw memory that we have to look at. This doesn't work. So that points to this data structure, which has quite a few different values, and then that ASN1 integer is a custom length data structure that they use for all primitives as well. And then within this, I discovered specifically what we care about is the public key. Also, sorry, just to step back, to give some more context, a lot of the checks in terms of validation on Java, conscript, all of those, let's say they do name validation or date validity checking and such, all of those typically get the values from the C structure through calling the OpenSSL or conscript functions. They don't actually store the values within the Java world, even though the certificate is initially requested within the Java world, transferred, stored in C. So they can have, or they can get those values, but in most cases they don't. A lot of the libraries, such as OKHTTP or such, those have, or TrustKit have extra checks. TrustKit, for example, stores it in an ASN1 data structure, and it compares the full ASN1 data structure of the two certificates, both the one it knows is true and the one provided by the server, to validate whether they are the same. So that gets complicated. We're not going to go into that. That's just to give context why I'm specifically looking into the C world. Because then, if I change the date values of validity here in the C world, that also affects the checks done in Java without having to hook or override or, in fact, worry about how any of those checks look, at least theoretically. Then, coming back to this, in this case, we're just looking for the public key. If we go first and we look now in memory, how does that look? On the left side, we still have that X509 info struct, and you'll see highlighted in color the different values of that. And then using Frida, we can see how those look within actual memory. And then from that, we can start to perhaps override or mess with these values. Now, going back to OpenSSL, we'll see that X509 public key is another pointer to another struct. You see a pattern here? Now we have another struct for the public key, and that contains another values with a lot of more offsets to what's called the P key value. And that goes to this struct, which has a lot of generic values to store a lot of different certificates. Because if you step back one moment, this is an X509 data structure. This is not specific to the public key. This data structure is not specific to the public key. This data structure within OpenSSL is designed to store any type of certificate. So private keys, public keys, in all different formats. So it has a lot of other values as well. And to be frank, to this day, I still have no idea what's going on there, because there's a lot of recursion going on there. And once again, yeah, as you can see there, the two important ones there is a stack of X509 attributes, which stores the actual attributes such as the dates, values, the names, and all of those of the data structure. So at this point, yeah, I took back a few steps back, because it's kind of becoming an infinite recursion almost here. And at any point in this process, if you are a single bit off, you completely lost. And you're not going to realize that until you get to the last value and try to read that. And if it's an integer, you might get a string and really not know what's going on. So for now, I'm pausing this. But the idea for me still is to try and find known values such as the certificate version and such, and trying to build up the data structure within memory, and then to be able to replace that full public key certificate. Then just as summary, what we've done so far and what we have seen. So we know if we have a black box application, we can establish the server that it connects to. We can get the hashes or public key keys that are possibly or likely used for pinning. Though keep in mind, the developer can obviously use some kind of custom hashing algorithm, and you're not going to be able to guess that, likely, unless you reverse engineer the application. So there's a lot of caveats here. But I think the base concept here is just that we have a potential different approach to patch certificate pinning, because all the base necessary information that we need, we have available or can get without looking at the core or without reverse engineering the application itself. And I believe this creates a bit of a different attack vector, especially for reverse engineering applications, not just for the not specifically for SSL pinning, but for a lot of other checks that rely on fixed length strings, so that we can patch them rather than having to hook the functions. Now, because we are working within memory here, there's a lot of difficulties and caveats. I've managed to crash my host machine quite a few times through this process, which theoretically should not be possible because I'm making memory changes within a virtual machine or Android virtual device. So that theoretically shouldn't be influencing my host machine, which might be worth investigating in itself. But yeah, throughout this process, I've had a lot of crashes because of the memory changes that I make. And that's it. Thank you. Any questions? Oh, I forgot something very important here. I'm not done, sorry. So I can actually show just a demo of how this actually works. So there we have our example application. I am just going to kill it, and then, if I'm on the right screen, we're going to start up objection. just loading our custom plugin in this case, and then we're starting the application here. Hopefully it'll start correctly. We're going to resume it. Yes, there's the application. So this virtual device is just set up to proxy through burp using the virtual device settings. We go over. And this is nice because we don't have to make any changes in the device itself. So that's just piping through to burp, which is running in the background. Now in this case, if we make unpinned requests, those are hopefully going to go through. But once we go into any of these pinned requests as expected, they are going to fail. So what we can do now is we can go back to objection. We can then, if I click, use the script that basically just implements the OpenSSL commands as I showed earlier, and that is going to. So this one is going to just pull the certificate hashes, both the raw and the base64 encoded, of the certificate chain, and then this one is going to provide us with the hash of our burp certificate, and then we can. In this case, we can, there's also a command to replace all of them, though in this case I'm just going to use the other command as I showed earlier to replace the hash within memory. So this one only does one specific one at a time, because there's only two, it doesn't really matter. So all we're doing here is we're taking the hash from the second one, the base64 one, we're searching for that, and we're replacing that with our burp hash. So as you can see, they found 13 matches within memory, and that is also partly due to how Java loads it into different places, but only one or two of those are actually important. Going back to the application, if we make that same request now, hopefully, all the thumbs, that is going to successfully go through. And if we go back to burp, we'll see those two requests going through and the responses. So yeah, that's it. Any questions on this one? Yes.
Will it work on a physical device?
Yes, this works precisely the same on the physical device. I don't want to have one yet to demo with, but the only reason I'm using a emulator here is because it's more repeatable, and I currently have a lot of other stuff on my physical device that makes it harder to test with. But yes, no, it works exactly the same on a physical device. Once again, in this case, I'm just using Frida, so you'd either use a Frida server on the router device, or just patching the application with either objection or manually with a Frida gadget.
So the catch is it needs to be rooted.
No, it doesn't need to be rooted. You can use you either patch the application with objection or Frida on a non-router device, or if you have a router device, you can use Frida server.
Okay, cool.
I don't see any other questions. Oh, there's one back there. It's a bit hard to see from here.
Hi, just a silly one. Those memory replacements that you're doing, is that just in the memory space of the hooked application? So it's not in the whole memory space of the device?
Yes, so that's a good question. In this case, it's only within even a specific part of the application. The application itself loads a lot of different libraries and such as conscript and such. But in this case, I'm only patching within the main application, though of course you can patch within the full context of the application, or if you're on a router device, you can also patch in the full context of the entire device.
Very cool, thanks.
I think that's all. Thanks.